My name is Jack Horsfall, and today I'll be talking about the influence of vortex generators on an aerofoil. This presentation looks at how vortex generators affect wing performance, particularly in terms of lift, drag, and boundary layer control. So, quick introduction. Aerodynamics is the study of how air and gases behave when they move and the force they create on objects moving through them. In aerospace engineering, understanding these forces is essential for improving efficiency, stability, and performance. At the moment, or currently, aircraft fuel efficiency is more important than ever due to high fuel costs and environmental concerns. So, reducing drag is one of the most effective ways to improve the efficiency of a wing or any object moving through air. So, affecting factors. The biggest factor affecting performance in flight is drag. For an aerofoil, drag can be separated into skin drag and form drag. So, form drag happens when the airflow separates from the surface, creating a wake behind the object. We can see form drag clearly in everyday examples. For instance, a large vehicle like a lorry produces a significant wake which shows high form drag, like in the picture. The boundary layer, this is just a quick overview of a wing. A boundary layer refers to the thin layer of air that sits directly on the surface of the wing. It is usually around an inch thick. So to understand drag reduction, you need to understand the boundary layer. This layer has much lower energy. The boundary layer has much lower energy due to the surface friction from the wing. The closer the air is to the wing surface, the slower it moves. To minimize separation and wake, airfoils are designed in a teardrop shape, encouraging the airflow to stay attached to the surface for longer. So, aims and objectives. This presentation will be looking at how adding vortex generators to a wing can improve lift and reduce drag in both aviation and other applications. It will be focusing on boundary layer control, wing aerodynamics, and drag reduction. And the idea is to be modeling a plain aerofoil and modeling a normal aerofoil, a plain aerofoil, modeling an aerofoil as plain and modeling an aerofoil with the vortex generators. And then through CFD and physical testing, we are able to see the differences and see that hopefully an increase in efficiency. So we'll focus on boundary layer control, wing aerodynamics, and drag reduction. So in order to create the designs, we had to model the aerofoils in CAD. This was done in simply just in Inventor, but this provided accurate geometry for computational testing and a 3D printed model for experimental testing. Here, these are the designs. So the first design is just a plain aerofoil. They are both the same aerofoil type, just modelled off a standard aerofoil example from aviation. And the second design, like I say, is the same aerofoil, but with the added vortex generators. Just of You can get vortex generators of different shapes, but for this example, we just use little square ones that are tapered off on the corners, so you don't get any disrupt over the vortex generators. And they are placed specifically on the wing at the same distance apart in a kind of V shape. So it's narrower at the front and wider at the back. So results and discussions. Multiple tests were carried out to evaluate performance of the vortex generators. One of the most useful comparisons was observing lift performance at different angles of attack using different vortex generator shapes. So we did do an example with an example has been seen with triangular vortex generators as opposed to square ones. And as the angle of attack increased, the difference between the different vortex generator types became clearer. So on this page, there's a couple of tables of rectangular and triangular vortex generators at different angle of attacks, and then the lift and drag forces recorded at a constant speed. So the simulation showed a clear performance gain with vortex generators installed. Triangular vortex generators were found to be significantly more effective than the rectangular ones. In fact, triangular vortex generators produced around 33% more lift at higher angles of attack, and up to 40% more lift at lower angles of attack. Additionally, the optimal placement of the generators changed depending on the airfoil profile used, and also the type of vortex generator used. I think there was just another bit there. As the angle of attack was increased through, just upgrade to angles of attack. So this is because I don't actually think it says it on the slide, but the vortex generators helped. This picture is a good example, so I wanted to talk about it with this picture on, even though it's a little bit blurry. But what an inefficient wing is what the top right picture looks like on the diagram, with like swirly air going over the top of the wing. That's when it stalls, and that's when the wing becomes inefficient. So the vortex generators help the air kind of stick to the wing for longer and at higher angles of attack. So just to conclude, vortex generators provided significant aerodynamic improvement, especially in lift generation. So the benefit is most notable at lower speeds, such as during takeoff and landing, where maintaining airflow attachment is critical, as, like I say, you can go at higher angles of attack when you're slower without the kind of curly effect happening on the air from uh, the air separating from the wing and then stalling over the top of the wing. At higher cruise speeds, the benefit reduces, but still offers measurable drag control and also slight improvements in efficiency. Overall, vortex generators are a simple, lightweight, and efficient solution for enhancing airfoil performance in a range of applications.